Welcome, this is Professor Ridge, and today's lesson 5.5, Zeros of Polynomial Functions. Our first learning objective for today, evaluate a polynomial using the Remainder Theorem. The Remainder Theorem, if a polynomial f of x is divided by x minus r, then the remainder is the value f of k. So, given a polynomial function f, evaluate f of x at x equals k using the remainder theorem. So your first step is going to use synthetic division, divide the polynomial by x minus r, and the remainder of that will be the value f of k. So this is an alternate way to evaluate polynomials using this remainder theorem. So if I wanted to find out f of 2, for instance, the traditional way is what we call substitution. You plug in the 2. Now if I'm using a calculator, then this is probably the way I would do it. But if I'm doing it by hand, I messed up there. Let me fix that. This is 15x squared. So again, this is substitution. So I would do, now if I'm doing it by hand, you're going to see that doing it using the remainder theorem is a lot easier. So 2 to the 4th is 16 times 6 is 96 minus 8. 4 times negative 15 is 60. Negative 60 plus 4 minus 7. Let's see, 96 minus 8. Let's do all the negatives. So negative 75 and then 100. So 100 minus 75 is 25. Okay, so that's substitution. Now watch. If I did it with synthetic division, I'm going, now this number x equals 2 is the same thing as dividing by x minus 2. So you switch the sign. But when you put in the synthetic division, remember you switch the sign. So if I divide by x minus 2, I'm going to do 2 in here. Okay, so this sign is the same. And then my my coefficients, 6, negative 1, negative 15, 2, negative 7. Leave her space for working. Bring the first term down. 2 times 6 is 12. Add down the column. 2 times 11 is 22. Add down the column. 2 times 7 is 14. 14 plus 2 is 16. Times 2 is 32. And 32 minus 7 is 25. And you can see that this is the remainder which is equal to 25, and by the remainder theorem, that's equal to f of plugging in this number. So f of 2 is 25. So now we have an alternate way to evaluate polynomials. We could do it the traditional way, substitution, and then alternate way is doing the remainder theorem. Now, by hand, obviously this is easier than this one in this case. With the calculator, I'd probably do it the bottom way, but there's some nice applications of doing it this way, which we'll get into in a minute. So I'm going to hold that thought. Okay, our next learning objective, use the factor theorem to solve a polynomial equation. Using the factor theorem to solve a polynomial equation. So what is the factor theorem? Well, it says that according to the factor theorem, k is a zero f of x if and only if x minus k is a factor of f of x. Okay, so if you plug in a value for f of x, for x into f, so if you do f of k and that equals 0, then x minus k is a factor of the polynomial. Right? So that's if and only if. So it works both ways. So how to? Given a factor in a third degree polynomial, use the factor theorem to factor the polynomial. So we're going to use the synthetic division. confirm that the remainder is 0. Write the polynomial as the product of, so if the remainder is 0, that means it's going to be a factor. X minus k is a factor. And then the quotient from that synthetic division will be the other factor. Okay? And if possible, factor that quadratic. Then write the polynomial as a product of factors. All right, so let's see how this works. So show that x minus 2. So you're told that x minus 2 is a factor of this polynomial, which means that if I plug in -2, that's the remainder would be 0. Or if I do the long division. So if I plug in, so remember you got to switch the sign, -2, and I got 1x cubed minus 6x squared minus 1x plus 30. Bring down the first term, -2 times 1, -2. Add down the column, -8. -2 and -8 make positive 16. Add down the column, 15. -2 times 15 is -30. And you can see that the remainder, so f of -2 is equal to 0. So that tells me that x plus 2 is a factor of the original function. Okay, so I can rewrite this polynomial, x cubed minus 6x squared minus x plus 30, is the x plus 2 times the quotient, x squared minus 8x plus 15. And then if I can factor this trinomial, then I can have it factored all the way out. So I want factors of 15 that add to 8. So that'd be 5 and 3. And then the bigger of the two factors gets the middle sign. That's the way I do it. And to get a positive 15, when I multiply, these two factors have to be the same sign. So that'd be x minus. Okay, now remember the zeros of the polynomial. So the zeros of the polynomial are, you're going to set this equal to 0. So you set it equal to 0, and then you set each of these factors equal to 0. And then you're not showing any work. Just remember, if you have x plus 2 equals 0, or let me write it over here, x plus 2 equals 0, you're going to subtract 2. So then you get x equals -2. So basically you're just going to switch all these signs. So the zeros are -2, positive 5, and positive 3. And then if you recall from the earlier when we were talking about graphing, if I were to graph this, the x-intercepts would be -2, 0, 5, 0, 3, 0. In fact, let me show you that. Okay, so I went into Desmos and put in the polynomial x cubed minus 6x squared minus x plus 30, and you can see that the x-intercepts are -2, 0, 3, 0, 5, 0. So the zeros of that polynomial will be those x-coordinates, -2, 3, and 5, which is precisely what we found here. -2, 3, and 5. Okay, so order doesn't matter. Okay, our next learning objective, use the Rational Zero Theorem to find rational zeros. Okay, the Rational Zero Theorem states that if the polynomial f of x equals a sub n x n plus, and then you got descending order all the way down to the constant term a sub 0. Those are integer coefficients, so that's important. And the leading term can't be 0, right? Then every rational zero of f of x has the form of p over q, where p is a factor of the constant term a sub 0, and q is a factor of the leading coefficient a sub n. Where the leading coefficient is 1, the possible rational zeros are the factors of the constant term. So we're going to take factors of the constant term, the last term, factors of the leading coefficient, and we're going to put them as fractions, where p is a factor of the constant and q is a factor of the leading term. Okay, so let's look at example 3. List all possible rational zeros. And again, rational numbers are just anything, any real number that can be written as a ratio of two integers. So basically 3 over 1, 3 over 2, 3 over 7, right? Those are either a nice fraction or a whole number or an integer, but you can't have like square root of 7 or pi, right? Those are irrational. Okay, so list all possible rational zeros. So again, by this, we're going to determine all the factors of the constant term and all the factors of the leading term. So, or P is going to be factors of the constant term, which in this case, ignore the negative, just do 4, factors of 4, and then we're going to put plus minus for all of them. So factors of 4, so basically that's 1 times 4 and 2 times 2. So 1, 2, and 4 are the only factors. Q is factors of the leading coefficient. So the leading coefficient is just 2. And then it's just 1 times 2 and nothing else. So just 1 and 2. So now our possible rational zeros are all the combinations of all the different factors for P and Q. So 1, 2, 4. So basically just do a system here. I'm just going to put, you could go start with the first one and put it over each of the Q's. So 1 over 1, which is just 1. 1 over 2, 1/2. Okay, that one's done. Now I'm going to go to 2. 2 over 1, 2 over 2, which reduces to 1. Oops. And then now we're going to do 4. So 4. So 4 over 1 and 4 over 2, which reduces to 2. And then you don't have to write the repeats. So all the possible solutions would be 1, and then you can do plus or minus. 1/2 plus or minus. 2 over 1, which is 2. 2 over 2 is 1, but I already have that. 4 over 1 is 4. Oh, don't forget the plus minus. And then 4 over 2 is 2, which is already there. So this is all the possible rational zeros. So there's eight possibilities. So what that does is, if I'm going to look for a 0, I'm going to just guess and check using these 8 things, and hopefully one of these work, and then I can divide it out, and then I'll have an x cubed left over. And if I'm lucky, another one will work, and then I'll have an x squared, and then I can either factor that the traditional way or use the quadratic formula. Okay. All right, so using the Rational Zero Theorem to find rational zeros. Use the theorem to find rational zeros of f of x equals 2x cubed plus x squared minus 4x plus 1. So our P is going to be factors of the constant term, which is just 1. And our Q's will be factors of so this is going to be our P's, and this will be our Q's. So factors of 2 is just 1 and 2. So all our combinations of P over Q will be 1 over 1 and 1 over 2. So we just have 4 possibilities. So to be zeros, we can do either synthetic division, or we could do just plug it in and substitution and find out if it's equal to 0. So either way, you can use synthetic division, or, okay, let's plug in -1. So 2 times -1 to the third plus negative 1 squared minus 4 times negative 1 plus 1. So we get, let's see, negative 2 plus 1 plus 4 plus 1. Let's see, negative 2 plus 1 plus 4 plus 1. So that's 6 minus, so that'd be positive 4, which is not 0. So negative 1's not a 0. Now we're going to try positive 1. So we just plug in the 1. So we get 2 plus 1 minus 4 plus 1. So 3, 4 minus 4 is 0. Okay, so that one works. Now we're going to try 1/2. So 2 times 1/2 cubed plus 1/2 squared minus 4 times 1/2 plus 1. So that'd be 2 times 1/8, which is 1/4, plus 1/4 minus 2 plus 1. So that'd be 1/2 plus 1 is 1.5 minus 2 is negative 1/2, which is not 0. Okay, and then our last one, f of negative 1/2. So let's see, we get 2 times 1/2 cubed, negative 1/2 cubed, plus negative 1/2 squared, minus 4 times negative 1/2, plus 1. So let's see, that's negative 1/8 times 2 is negative 1/4, plus 1/4. That's nice, that's 0. Plus 2, plus 1, so that's 3. Which is not 0. So our only 0 is 1. So x equals 1 is the only 0. Well, the only rational 0. There could be irrational zeros. In fact, there's 2 of them. So if I plug in, if I did the synthetic division thing to find the quotient of dividing out the x minus 1, and then I can use the quadratic formula to get the irrational zeros. So x is the only rational 0. Of f. And our next learning objective, find zeros of a polynomial function. Okay, how to. Given a polynomial function f, use synthetic division to find its zeros. Use the Rational Zero Theorem to list all possible rational zeros. Use synthetic division to evaluate a given possible zero by synthetically dividing the candidate into the polynomial. And remember, if you get 0, the remainder is 0, then the candidate is 0. And if the remainder is not 0, you discard the candidate. Okay, and repeat steps 2. Using the quotient found with synthetic division. If possible, continue the quotient is a quadratic. So basically we got to keep looking for zeros until we get down to a quadratic. Once you get to the quadratic, you find the zeros quadratic function one of 2 ways. You can use the quadratic formula or just factor the trinomial, just the normal way. Alright, so let's try this. So we got 4x, so our possible rational zeros would be, so p is going to be just 1, q is going to be 4, so we got 1, 2, and 4. So when we start with our list, and remember we're going to do plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 1 over 4. So we got 6 candidates. So we start with 1. You can check 1 without doing synthetic division, just by doing, remember when you put in 1 to any power is just 1. So basically you're just going to check the coefficients. 4 minus 3 minus 1 is 0. So we know that 1's going to work. So when I do it in my synthetic division, it's going to get me 0 as my remainder. So remember, you have to do descending order. Any missing terms, you got to put a 0. So if this is x cubed, 0x squared minus 3x minus 1, and then bring down the first term. 1 times 4 is 4. Add down the column. 1 times 4 is 4. Add down the column. So negative 3 plus 4 is 1. And then 1 times 1 is 1. Negative 1 plus 1 is 0. So we know that our polynomial now is f of x is equal to x minus 1. And then this is x squared, because this was x cubed divided by x gets me x squared. So 4x squared minus 4, oh no, plus 4x plus 1. So I can continue this process by, looking to see if 1 would work again or whatever. But if this is a quadratic, I can just use quadratic formula, or if I can factor it. Hopefully you recognize, oh, that's a perfect square, right? This is 2x plus 1 squared. If you recognize that. If not, you got to do the factoring techniques that we learned in an earlier chapter. Okay? So then our zeros are, so we're going to set this equal to 0 and then solve it. So the zeros are 1, and then remember you're going to subtract 1 and then divide by 2. So it's 1/2 negative, and then negative 1/2 again. So we got negative 1/2 with a multiplicity of 2. So if you recall, if I were to do the graph of this, this is x cubed. The leading coefficient's positive, so the ends go like that. It's going to hit at 1 and a negative 1/2. So if I was on 1 and negative 1/2, so what's going to happen is negative 1/2 is a multiplicity of 2, so it's going to bounce. I can figure out what the y-intercept is. Somewhere it's going to bottom out, and it's going to cut through there. So my graph will look something like that, kind of tying together all the concepts we've covered up to now. All right, so let's check on Desmos and see how that works. Okay, so you can see 4x cubed minus 3x minus 1, and you can see it bounces at negative 1/2 or negative 0.5, and it cuts at 1, right? So we get the x-intercepts are negative 1/2, 0, 1, 0. The y-intercept's negative 1. So remember, if you put in x is 0, you get y is negative 1. And when you go on to calculus, you'll learn how to figure out this point without guessing and checking. There's a way to do it. Okay, it's called taking the derivative, but again, that's for another class. So anyway, for this class, we won't be able to figure that out. We can kind of guess it, but that's about it. Using the fundamental theorem algebra. The fundamental theorem algebra states that if f of x is a polynomial of degree n greater than 0, then f of x has at least one complex 0. We can use this theorem to argue that if f of x is a polynomial of degree n greater than 0, and a is a non-zero real number, then f of x has exactly n linear factors. So basically you can take any polynomial, and if you're allowed to use complex numbers, you can take any polynomial degree n and split it up into n linear factors, right? And so C1, C2, Cn are complex numbers. Therefore, f of x has n roots if we allow for multiplicity. So the roots would be if you set this equal to 0 and solve that equation, right? So n roots. Okay, example 6, finding zeros of polynomial function with complex zeros. So find the zeros of f of x equals 3x cubed plus 9x squared plus x plus 3. So what we're going to do is look for rational ones first. So we're going to take, or or possible p's over q's. So p could be factors of 3, so 1 and 3. Q can be factors of 3 as well, so 1 and 3. So p of q would be 1 over 1, which is 1, 1 over 3, 3 over 1, and 3 over 3, which is 1. And then you get to do the plus minus. So this is what we're going to start with. So if we did 1, you get 3. So 1 won't work, so 1's out, because it's not going to be 0. If I do negative 1, we get negative 3, 9, negative 1, 3. Negative 1 won't work. So basically what I'm doing is in my head just plugging it in to seeing if the remainder is 0. Or you could do synthetic division. Either way. So just to show you what I was... So 3, this would be negative 3, which is 6. Negative 6, which is 5. Negative 5, which is negative 2. So it's not 0. So 1 didn't work, negative 1 didn't work, so now we're going to try 1/3. And since these are all positives, I'm going to go with a negative number, because it'll just keep adding and you won't get to 0. So we need a negative in there. 3, 9, 1, 3. And then we bring down negative 1/3 times 3 is negative 1. So negative 8/3. So this, think of 1 as 3 over 3, so that's negative 5/3. So 5/3. Okay, it's not 0. Okay, so now I'm going to try negative 3. So 3, 9, 1, 3. Negative 9, so that's 0. Negative 3 times 0 is 0. Negative 1 times, or 1 times negative 3 is negative 3. Okay, that one works. So now we can factor our polynomial into x plus 3. Remember, you got to switch that sign. And then this is x cubed, so this would be x squared. 3x squared plus 0x plus 1. Now I want to find the zeros, so I'm going to set this equal to 0. So I set this equal to 0. So x equals negative 3. 3x squared plus 1 equals 0. So x squared equals negative 1/3. And then I square root both sides. Plus or minus square root of negative 1/3. Which is, remember the negative is the I. And then you got to rationalize square root of 1 over square root of 3. You got to rationalize the denominator. So you got to multiply it by square root of 3 over 3, which will get me square root of 3 over square root of 9, which is just 3. Square root of 9 is 3. So the negative is the I, and then I have the square root of 3 over 3. Okay, so my zeros of this polynomial, you can say f or f of x. I prefer to say just f, but the book does f of x. Same thing, kind of. Negative 3, comma, I square root of 3 over 3, and negative I square root of 3 over 3. And notice these are what we call complex conjugates of each other. So if you have a complex number that's imaginary, if it's not real, so 3 is a complex number, but it's also real. Complex is all the real numbers plus all the real numbers attached to, this form, a plus bi, where a is a real number, b is a real number, I is the imaginary unit. So anything that can be written in this form is considered a complex number. So if it's like 3, negative 3, that's negative 3 plus 0i. But if b is 0, then this is what we call it's a real number, right? It's purely real. If a is 0 and you got bi, then it's purely imaginary. If you got a and a b with the I in there, then we just say complex number. So it has a real part and an imaginary part. So if it has an imaginary part, they always come in conjugate pairs. Okay, on to the next learning objective. Use the linear factorization theorem to find polynomials with given zeros. Okay, so the complex conjugate theorem, according to the linear factorization theorem, a polynomial function will have the same number of factors as its degree. Each factor will be in the form of x minus c, where c is a complex number. So if the polynomial function has real coefficients and a complex zero in the form of a plus bi, then the complex conjugate of the zero, a minus bi, is also a zero. That's what I was talking about in the last example. They always come in conjugate pairs. Okay? So if a plus bi is a zero, then a minus bi is also a zero. Okay, using the linear factorization theorem to find a polynomial with given zeros. So find a fourth degree polynomial with real coefficients that has zeros -3, 2, I, such that f of -2 equals 100. So our first step is use the zeros to construct linear factors of the polynomial. So f of x is going to be x minus a -3, so that becomes +3. Remember, you just change the sign. X minus 2, and then x minus I. But remember, from what we just talked about, they always come in conjugate pairs. So if I have 0 plus 1i, I get its partner, 0 minus 1i. So minus I. And then you put it, it'll be x minus, so you got to switch it, minus a minus, becomes plus. Now we're going to multiply these linear factors to expand. Oh, I forgot the a in front, because we want f of -2 to be 100. So we got to figure out what that a is using this initial value. Okay, so multiply it. So here's the way I do it. I'm going to multiply the complex ones first. And remember this form, a plus b times a minus b. It's just a difference of squares. Those middle terms will cancel out. Okay, so I'm going to FOIL the first two. So I'm going to FOIL these. X squared minus 2x plus 3x minus 6. This is a difference of squares, so it'll be x squared minus I squared. But remember, I squared is -1. So minus a -1, that's going to become, okay, hold that thought. X squared, I'm going to combine like terms, so it'll be plus x minus 6. X squared minus a -1 becomes +1. Now what I need to do is multiply these two parentheses. So I can do that in scratch work if I want, or I can do it right in the problem. Let's do it in scratch work here. Let me erase all that. Okay, so I'm going to do x squared plus x minus 6 times x squared plus 1. So I'm going to distribute the first term with both of these. So that's x to the 4th plus x squared. Then I go to the second term, distribute it. So there'd be x cubed plus x. Then I go to the third term, distribute it. So -6x squared minus 6. And then combine my like terms. X to the 4th, now x cubed. X squared, -6 plus 1 is -5. X minus 6. Okay, so just those two terms combined. Everything else, just wrote them down. Okay, And then I have this a out in front. So now, so f of x is equal to a x to the fourth plus x cubed minus 5x squared plus x minus 6. Now I'm going to plug in -2 for all my x's, and that's going to be 100. So 100 is going to be -2 to the fourth plus -2 to the eighth minus 5 times -2 plus -2 minus 6. Punch that in my calculator, so hang on. Oh, I noticed when I was punching it into my calculator, that would be a 3. I was thinking -8, so I wrote 8. Okay, so we get, what was it? I got -20. So a times -20 equals 100. And then I'm going to divide both sides by 100. I mean by 20. So a is going to be equal to, divide by -20, -5. So now that I know a, f of x, and then I can just distribute -5 on this one. So -5x to the fourth. I'm going to run out of space here. Here, let's just move it up. So -5x to the fourth, -5x to the third, plus 25x squared, plus 25x squared, minus 5x, and then plus 30. And that will be my answer. Okay, on to the next learning objective. Use Descartes' Rule of Signs. According to Descartes' Rule of Signs, if we let f of x equal a sub n x to the n plus a sub n minus 1 times x to the n minus 1 plus ... plus a sub 1 x plus a sub 0. So again, this is just the notation saying it's polynomial in descending order. So it's a polynomial function. Coefficients have to be real. The number of positive real zeros is either equal to the number of sign changes of f of x or less than the number of sign changes by an even integer. The number of negative real zeros is either equal to the number of sign changes of f of -x or is less than the number of sign changes for an even integer. So if you recall earlier, we did a problem and we were doing it. It said all the numbers were positive, and I said, okay, I'm going to try negative. I was actually using this rule when I said, because if f of x, if all these are positive, so 9, I don't remember the numbers, but we can go back and look, but it doesn't matter. So if it's something like this, something like that, if I look at the signs, this is positive, 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 and if I'm looking at the number of sign changes, so there's going to be 0 sign changes, right? So we're looking from flip-flops from positive to negative. So since there's 0 sign changes, this rule tells me there's 0 positive real zeros. So if there's going to be some real zeros, they have to be negative. Okay, and then when I do the negative, if I put in f of -x, so this was actually the rule I was using. I didn't tell you that, but that's what kind of led me to say, hey, let's look for some negative ones. So then this would be, so when you do a negative x to n, you're going to do -1 to the n, x to the n. So if this is an even power, if it's even, you're going to get the negative becomes positive 1 times x to the n. If it's odd, if this is odd, you're going to get negative x to the end. Okay? So this is odd, so this negative comes out, and I get negative 9x cubed. This one's even, so the negative cancels. This one's odd, so I get negative 9x. And then there's no x here, so that one stays the same. And notice you got negative, positive, so there's a sign change. There's a sign change. And there's a sign change. So that has 3 sign changes. So f of x has 3, it has up to 3 negative real zeros, or 3 or 1 negative real zero. Okay, so that's how we use it. And there's 0 positive ones, so don't waste your time looking for positive ones. There's a possibility there's at least 1 negative. Now, real doesn't mean it's going to be nice, right? It could be square root of 7. But there's at least 1 real 0. There might be 3, so it's 3 or 1. But there's definitely no positives. All right, let's try the example from the book. Okay, example 8, using Descartes' Rule of Signs. Use Descartes' Rule of Signs to determine the possible number of positive and negative real zeros of f of x. Okay, so for f of x, for our positive real zeros, we're going to leave this alone. So we got negative x to the 4th, negative 3x to the 3rd, positive 6x squared, minus 4x, minus 12. And we got negative, okay, positive. So there's a flip-flop, positive to negative. There's our second one. And then that's it. So just 2 or 0 positive real zeros. Okay, now we're going to do the negative one. So we're going to do f of negative x, which is negative x to the 4th, negative x to the 3rd, negative x squared, negative x. And from what I showed you before, the even ones, the sign cancels, so it'll be so this negative cancels, and it'll just be negative x to the 4th. This one, the sign, it's odd, so it'll be negative 1 that comes out times this negative, so that one switches to 3x to the 3rd, right? So negative 1. Let me just show you all the work that's going. So we rewrite it like this, and this is negative 1 times negative 3, which becomes positive 3. But if it's even, negative 1 times negative 1 would be positive 1 times 6 would be positive 6. So the shortcut, if it's even, leave the sign alone. If it's odd, switch the sign. So this one's even, leave that sign alone. This one's odd because it's to the 1st, so it switches. I don't know if that helps you, but that's the way I think of it. So we're looking for flip-flops from positive, negative, or vice versa. So negative to positive, that's 1. Positive to positive doesn't switch. Positive, positive doesn't switch. Positive, negative, that's our second one. So we have 2 or 0. And you just subtract 2 till you get to 1 or 0. So if I had 7, it would be 7, 5, 3, sorry, 7, 5, 3, 1, and then you stop at 1. Okay, so 2 or 0 negative real zeros. Right, so possibility 2, possibility of 0, but no other combination, right, 2 or 0. So this can have, basically have 2 positive, 2 negative. It could have 0 positive, 0 negative, and then that would leave 4 complex, right? Imaginary ones. So whatever's left over to get 4, because degree 4, those would be imaginary. And remember, imaginary always come in complex pairs, so that's why we're dropping by 2 on these combinations. Okay, the book put this table out. I thought it'd be useful to mention it. So what I was talking about, so all the combinations of zeros, you can have 2 positive, 2 negative, so that would leave you 0 complex, because you're always going to get a total of whatever the degree n is. So in this case, it was x to the 4th power. Okay, so then the other combination, another combination could be, you can have 2 positive reals, 0 negative reals, so that leaves you with 2 complex to get a total of 4. You can have 0 positive, so remember the combination is 2 and 0 for both. So then just, if you have 2 choices, that gives you 4 combinations. So 0, 2, then that leaves you 2 for your total of 4. And then the last combination, you can have 0 positive, 0 negative, then that leaves 4 complex to get the total of 4. Okay, and on to the last learning objective, solve real-world applications of polynomial equations. Okay, solving real-world applications, example 9. A new bakery offers decorated multi-tier cakes for display and cutting at quinceañeras and wedding celebrations, as well as sheet cakes to serve most of the guests. The bakery wants the volume of a small sheet cake to be 351 cubic inches. The cake is in the shape of a rectangular solid. They want the length of the cake to be 4 inches longer than the width of the cake, and the height of the cake to be 1/3 the width. What should the dimensions of the cake be? Okay, rectangular solid is from that first read, rectangular solid. So let me make my rectangular solid cake. So let's see, I want volume to be 351 cubic inches. Right, inches cubed, cubic inches, same thing. Okay, and let's see, they want the length cake be 4 inches longer than the width. So the length, so let's call this x, and this will be x plus 4. And length, width, and then the height of the cake will be the height of the cake to be 1/3 the width. Okay, so my scale is off a little bit. So 1/3 x, but that's okay, just to get the box shape. So basically be down like this. Anyway, so now for our volume is going to be length times width times height. So be 1/3 x times x times x plus 4. And then that's going to be equal to 351. So we're going to multiply this out. So 1/3 x cubed plus 4/3 x squared equals 351. And now we want to solve this. So let's multiply everything by 3 to get rid of this fraction here. So if I multiply everything by 3, x cubed plus 4x squared equals 351 times 3. Okay, that's 1053. Okay, so now I want to solve this. Here, let's move it up to here. So I got x third plus 4x squared minus 1053 equals 0. And then we're just going to look at factors of this one to see if I get any zeros. So let me try. Okay, so we know that 3 times, so I'm just going to factor here. So it's 3 times 351. I think another 3 comes out of here. 3 times, see, 117. I think that's right. 117, and another 3 is going to come out. So that would be 3, 9, and another 3. So I'm going to try like 3, 9, 27 in here. So remember, if it's something rational, it's factors of this over 1. So I'm going to try 3. 3 doesn't work. I'm going to try 9. So 27. 8. Let's see. I think that's going to work. Let me try it. So if I try 9 cubed, 4 times 9 squared minus 1053, does that equal 0? Yes, it does. Okay, so 9 is the solution. So x needs to be, what should be the dimensions of, so x equals 9. So 1/3 of 9 would be 3. And then 9 plus 4 would be 13. So the cake should be 13 by 9, and these are inches, by 3 inches. Oh, I already wrote inches. All right, so that is our solution. Okay, and that brings us to the end of the lesson. So again, practice, practice, practice. So go to the end of that exercise set, do all the odds or as many as you can, and then if you have time, do some of the evens too. All right, have a great day. See you next time.